Thank you. Well, welcome. This presentation, it's about Bloom filters on Redis. As he said, my name is Cristian. I work for Scopely. We are a game publisher and game studio company based in Los Angeles. We're focused mainly on the free-to-play mobile game market, and we have some games in our portfolio like Walking Dead, Yahtzee, WWE, etc. And the context of this presentation is in stream processing, okay? And it's basically a success story, a use case where we were able to reduce memory consumption and latency by almost tenfold, okay? So I'm gonna have to give you a little bit of background and context on how things work at Scopely. So we have basically millions of devices that have installed the games. And these devices are constantly sending data to our collection layer. So this is an HTTP endpoint, and they send events like a user opened the application, they saw an advertisement, they killed a zombie, they, I don't know, reached certain level, etc. Okay? And once we get these events, we dump them in a stream. In our case, we use Kinesis. All of the infrastructure in Scopely is built on top of Amazon. So Kinesis, for those who don't know, is similar to Kafka, but it's managed by Amazon. So we have the first application is an enrichment layer, where we take all these events, we add more information to this based on what we know about the users, and then we write that back into a different stream. And from here, there are many applications reading this stream. So we have real-time metrics aggregations for dashboarding. We have data warehousing, Elasticsearch indexing, etc. Okay. Now, if we zoom in into how these streaming systems work, we'll usually have basically an append-only log, which is constantly receiving data from a producer, right? And you have multiple applications that can have multiple workers reading batches of this data, right? So in Kinesis, you can read up to 10,000 records at a time. And here's a difference between a streaming processing system and a PubSub system. And it's basically that the consumer, the application, is responsible to keep track of where in the stream it is currently reading from, right? So for that, you usually use a checkpointing table. So this is basically a mapping between your stream and what's the latest record you have processed so far, okay? So let's say in this case, you read the first 3 records, and then you write down in this checkpointing table, hey, I've read so far until record number 2, and then you keep reading, etc. Right? Another reason why you do this is because sometimes these applications can go offline. They could crash, or you can deploy a new version of your application. So another worker will come and replace this one, right? And it needs to know where to read from, right? Now, ideally, when your consumer is reading a batch of events, it's going to produce certain output, right? So it's like it's going to do enrichment or filtering or whatever. What happens and what could happen is that if for some reason you process one of these events, you did the processing, and your consumer crashes, then the next time it catches up, the same batch, there's potential for it processing the event more than once, right? And this is something that you don't want to happen in your stream processing systems. So what usually companies end up doing is implementing what we call an idempotence layer, okay? So idempotence, or an operation that is idempotent, is one that you can apply it multiple times and it has the same effect, okay? In the context of stream processing here, what we're saying is basically we don't want to process a record more than once, okay? Now, the simplest way to do idempotence, and this is something that we do at Scopely, is using Redis sets, okay? So in a Redis set, what you do is that every time you're going to process one of the records, you go and check in this idempotence store, in this set, to see if the ID of the record is already there. If it's not there, it means you haven't processed it yet. You go process it, and you save the ID of the event in the set. So in the event that this thing crashes, and you get the same batch of events, you won't have duplications, right? Because you first have to check in this set if something was processed already. Now, obviously, you cannot keep growing this set forever because you are in the streaming world where you're potentially having infinite streams of data, right? So what you end up doing usually is having like this rolling group of sets where you're writing to just the latest one. You keep one just for reference, and the next day you start writing into a new set, and the previous one will eventually expire. So that's all cool. In production, it looks a little bit like this in terms of memory usage. This is a sample of one of our applications. So it uses around 70 gigabytes of memory just for the idempotence in 300 million records. Okay? Now, take into account that this is just one application, and every single application reading from the stream needs to have its own idempotence store. Okay, so in the case of Scopely, around 6 to 8 applications doing different stuff at different paces. So you multiply that by 70 gigabytes, and that's how much we use just for idempotence in Redis. Now, the question is there a better way to do this? Right? Is there a way that is more space efficient, and because of that, it's cost effective? So Redis memory is by no means cheap, so the less you use is the better. We also want to reach a point where it's more performant. As we add more games to our portfolio, we want this to not get slower and slower, right? And is there a way that is awesome? And yes, there is. Bloom filters. So how many of you have heard about Bloom filters? Quite a lot. Not surprised. So Bloom filters are quite old. They are almost 50 years old now. They were invented in 1970. And Bloom filters are basically a probabilistic data structure that allows you to check if an item is a member of a set or not. Okay? Now, the key word here is probabilistic. When you see probabilistic in a data structure, you know something's going on, right? So in the case of Bloom filters, when you query a Bloom filter, you get two answers. You get either, hey, this item is not in the set at all, or it's probably in the set. Okay, so there's room for error here. One interesting thing about Bloom filters is that this error rate is configurable at the moment that you create the filter. Okay, so just to give you a perspective on how efficient they are space-wise, let's say you have 10 million IDs and you want to do some sort of idempotence or something. If you were to use Redis sets, plain sets, it would be around 1 gigabyte of memory, right? If you just put it in a plain text, just for the sake of experimentation, it's around 300 megabytes. Even if you compress this thing, it's about 150 megabytes. If instead you use a Bloom filter with an error rate of 1 in a million, you're talking about 30 megabytes. Now, this is a huge improvement in the space, right? Now, it might be that 1 million is too much of an error rate. So let's say 1 in a million. Now you have only 60 megabytes. So it's a little bit bigger, but keep in mind that this 1 in a million means that you're going to get a false positive 1 in a million times of queries, okay? So this is very, very, very impressive. If we compare this is actually a comparison of the same application where we are running idempotence using both modes, just to see how they look like. The Bloom filters is the red line. It's basically 7 gigabytes all the time, okay? Compared to 70 gigabytes of Redis sets, that's a very impressive improvement, right? In terms of latency, Redis sets is around 2 milliseconds per operations most of the time. With Bloom filters, you have under 0.25 milliseconds. That's also almost 8 times an improvement in latency. So that's very, very impressive. So the question is, how do they work? Like, how is it possible that they are so damn fast? So the idea with Bloom filters is that when you are adding things to this filter is basically a bit set, okay? So imagine this, a big chunk of bytes, right? And when you are adding things to this filter, you hash this item, and this hash represents some bits in this filter. And what you do is you turn on this filter, these bytes, these bits. When you want to check if an item is part of this set, what you have to do is to check if these bits are on or off. If one of them is off, at least you know that the item is not there, right? But because the space is shared, there is a chance that as you keep adding things to this filter, you can get false positives. Now, I tried to come up with a very simple example of how they work. And it's an example that you can use with your coworkers or with your boss. And you just need paper and pen to do it. So it's very interesting. Let's see. Let's assume this square represents a Bloom filter. It's empty right now. So let's imagine that we're going to start adding items to this filter. And for some reason, this first item, the bits in the set, we're going to represent them as pixels, right? So the first element, when we want to insert it, is going to look like an A, okay? And what we want to know is if this element is potent or nullipotent. Potent meaning that we have not seen it before, and hence we have to process it. Nullipotent meaning that we already saw it, and we're going to ignore that event. So in this first case, it's very simple. It's empty, so we just add the element directly to the filter. We know it's potent, right? Let's see B. If we want to add B here and to see if it's potent or nullipotent, well, all the pixels of B are not already used in this filter, so it's also potent, right? Now, the first interesting case is C. Now, if you see all the pixels that conform the letter C are already used in this set, which means that when you ask this Bloom filter, hey, is C part of this set, it's going to tell you, probably. And then you can keep repeating this same example with all the letters. And at the end, you're going to have something that looks like this, right? So we have 5 elements that were nullipotent. The set is going to look like this. And from this, you can infer some conclusions. The first one is that the more items you add to the set, the higher the probability of getting a false positive is, right? The second thing, and very important, is that just by looking at the set, it is impossible to know what items it holds, right? So, and that's what makes it different from a regular set. In a set, you can usually enumerate or list all the items of your set, right? In this case, you cannot. You have a shared space of memory that holds everything, and everything is overlapping, okay? So hopefully this was useful. And I have to do a big remark here. In the context of streaming processing, a false positive means basically that you're dropping data. And this is a very important caveat that you have to take into account before you even think about using this in production, right? In the case of Scopely, there are many things to take into account. The first one is that most events we received come from non-payer users, right? So we are in the free-to-play game market. So the less memory we use, the better. But also, most of the data that we receive is used for analysis purposes, right? And because of that, dropping a few events every day is not a big deal. It's statistically meaningless, right? So we can afford to drop some data. But you have to think carefully about your specific use case, because sometimes that might not be the best way to go. Now, a Bloom filter has basically 2 things. It has a capacity and an error rate probability. And you can think of this as a contract between you and your filter. What the filter is telling you is, as long as you don't use these many items, as long as you don't reach this capacity, I'm going to assure you that the error rate probability is going to be this or less, okay? Now, the question that follows is, okay, what happens if I exceed that? Because let's say I get more events one day. There's a spike of events. So there's this other data structure that is kind of like a modification of Bloom filters called scaling Bloom filters. And this is what most implementations do, right? So a scaling Bloom filter is one that once it is full, it's going to create another one on top of it, okay? And you can keep adding things to this one. And when it's full, it's going to keep creating more and more filters. Now, of course, every time you add an item, you add it to the last one, right? But when you check for memberships of an item in the set, you have to check all of them, right? And this is important to keep in mind because it basically increases latency, right? So you don't want these things to keep scaling. Now, that's why it's very, very important to tune these filters correctly, okay? The size of the filter depends on its initial capacity and its error rate probability. If you remember when we decreased the error rate by 1,000,000, the size of the filter basically doubled, okay? So since you want to achieve, to reduce the size and reduce memory usage, you need to make sure you're tuning your filters correctly. So the first thing is false positives. And this is, of course, depends entirely on your use case, and it's probably non-negotiable. So you said what your expectations of the filter are, and you need to stick with this, right? The other is the capacity, and here you cannot be too generous, because if you set your capacity too high, what happens is that you're going to be wasting space, right? Because if you don't use that much, when you create a filter, you're basically allocating a chunk of static memory, right? So it doesn't matter if you don't use it all, it's going to be there, used, okay? Now, if you're too conservative, on the other hand, what happens is that your filter is going to keep scaling and scaling, and that's going to introduce latency, and it's going to probably give you at the end, again, more space than what you need. So you need to to know your data, basically. What we did in our case was that we were running the old idempotence thing at the same time with Bloom filters, so we were able to tune them on the fly to find that point where we don't scale. That's why that graph before was, the Bloom filter size was flat. It never scales. It just kept the same size ever. And it uses about 80% of its capacity at all times. Now, let's see how we can actually use this in Redis. So the first thing we tried was using Lua scripts, okay? So a refresher, Lua scripts are a way that Redis gives you to script like custom behavior on your cluster. So you load a script that you can then execute, etc. Now we did the implementation of Bloom filters using Lua scripts, and they are actually not performant enough. So that was a few years ago. So we went back to just regular sets. The next thing we tried, and this is not in Redis, it's called BloomD. Now BloomD is a very interesting project. It's an implementation of Bloom filters in C, and it's basically like a server. It works like Redis, basically. It exposes a TCP/IP connection, listening, and then you connect to it. You can create filters, add filters, check filters, and it's good. And it's performant, of course. Now, it has a few drawbacks. So there's no high availability concept here, so there's no like a master-slave thing and fault tolerance or anything like that. There's no clustering, so if you want to distribute the load of this between different machines, you have to do it all by hand, which is very cumbersome. You have to maintain these things yourself, right? There's no Redis labs for BloomD. There's nothing like that. So you need to keep this up and running yourself. It also has a very rigid API, and it's very cumbersome to work with sometimes. And it's also like the author of this is very important guy in this industry, and he's very busy too. So he built this, and he was like, yeah, this works. Go guys, use it, and I'm done with this. I'm going to go work on something else. So it's unlikely that any of these things are going to be improved anytime soon. So that brings us to RedBloom. And this is basically what the talk was about. So RedBloom is an implementation of Bloom filters using Redis modules, okay? when you add it to your cluster, when you load it, what you have is a way to create filters, yeah, with a specific error rate and capacity. And then you have commands to add things to this filter or to check for items in the filter. There are also versions to add in bulk or to check in bulk. And it's very simple. Now, this has very advantages over Bloomd. The first one is that, of course, because you're writing on top of Redis, now you have all of a sudden high availability and clustering and all that good stuff, right? It also has a lower cognitive overhead because, of course, like most people, at least in Scopely, are already using Redis. So this is just a matter of learning a few more commands, right? You can still use your same clients and everything. It's just very easy to grasp. The API is way more powerful, more expressive, and it allows you, like, when we moved from Bloomd to RedBloom, the code base of the implementation of this was reduced by almost half. So that's nice, too. In our case, we use Redis Labs, so we don't need to maintain these clusters, and that's also a relief, because it is very scary to run Bloomd in production because you don't know if it's going to crash or not. And it's something I don't recommend. So this is basically it. Here's two takeaways I want for you to go with. The first one is that Bloom filters are very interesting. They're very old data structure, but they are relevant today as hell. So they can reduce the memory usage by a lot, and the latency also by a lot. So this is something that you should take into account if you have a use case similar to what I was discussing, right? The second thing, which is a little bit more implicit, is that Redis modules are a very interesting way to take a data structure that is somehow very customized and make it scale, right? And the example is right there, like with Bloomd. Bloomd was designed specifically for Bloom filters, and it's written in C, which means it's super performant. And even though that's the case, it doesn't give you as much as RedBloom because this thing is built on top of this machinery called Redis. So this is a very interesting thing to take into account. So this is my website. I'm going to be publishing these slides there. There's also a complimentary blog post with more information about like how the transition was made, etc. You can reach me by email. It's somewhere in the website, and this is my GitHub handle. And that was very fast, actually. Maybe I was talking too fast. So if you have questions.
Thanks, Christian. Now we have lots of time for questions. First one over here.
So you did mention that you're saving space by using Bloom filters. But what if I really want to use the data? So you're using sets, and you're using Bloom filter to filter. But I really have the need to use the data, so I still at some point have to use the sets, right? So at that point, I don't really see why I need to use a Bloom filter when I can just leverage the set.
Yeah, that's a fair question. Well, the answer is that data is not needed, even if you use sets in our case. When you're working with idempotence, what you're doing is you just want to keep track of stuff that you already processed, right? It's not a data store that you want to use to go and check for data and retrieve that data. This is just a layer between your application, right? Between the stream and whatever it is the output of the stream, right? So when you're talking about idempotence, then it's okay. Like you don't need to query this data. This is mainly so that you don't repeat yourself. So I hope that answered your question. Of course, once after the idempotence phase, then is when your application actually does something, like it writes to Elasticsearch, or it saves data to S3. So that's where your data is going to be. And you know that data there is going to have no duplicates. So that's also one of the reasons you want to use this.
Do you do any time-based cycling of your Bloom filters in order to keep them clean?
We use the very same technique that with Redis sets. So what we do is we hold all of our keys of today's data in UTC time, ingested the data, okay? And when you create these sets, you set the expiration to 24 hours. So when the next day comes, you start writing to this new set, you still have the previous day of data there, and you check in both, of course. You need to check that the item is not present in any of them. And eventually, Redis will expire those, and you're fine.
So are Bloom filters mainly used to weed out negative results? Because if there's a lot of positive like requests going in and asking if it actually exists, and you're trying to like minimize the amount of memory you're using, the worst case scenario will come up a lot more often.
No, well, so you're saying that over time there will be more false positives than you expected?
It's just that I'm just wondering if Bloom filters are mainly used for to weed out negative results versus positive results.
Yeah, it's more for the negative part. Yeah, that you want to know what is not there. Like that's the main use case, because what is not there is what you need to process. So yeah.
So I read that Bloom filters cannot produce false negatives. That basically, if it says not there, it's definitely not there.
Yeah.
So if that's the only thing you're using, then there is no error rate in that case.
Well, for that, there's no error rate, yeah. When it tells you that something is not there, you're 100% it is not. And the reason you know that is because in the case of the example of the pixels, well, you know that if part of that square, part of the set has the pixels of the item is not on, it means that you never added anything like that. So you know for a fact that that item was never in the set in the first place. So that's why that part has no error rate probability at all. It's just when it tells you that there is something there, there's false positives there.
And sorry, my other question is, you mentioned that underneath the hood, it's just hashing the items in the sets.
Yes. So the implementation is, of course, a little bit more complicated than I'm making it sound. But basically, this chunk of data, like depending on the error probability, there are many hash functions that it uses underneath, okay? And it does that with, like, basically it takes your item and passes it through a bunch of hash functions. And that gives you a bunch of random IDs, like random but like deterministic bits in different positions on the resulting set, okay?
The error rate is basically completely dependent on the hashing function that's being used and their collision rate.
Yeah, but in the case of RevBloom, well, when you create a filter, like underneath, there's like a command called bf debug, where you can see things like how many hash functions it is using, what's the real size of the set, etc. But basically, the error rate probability depends, of course, on the size of the filter and how many hash functions it is using, right? So, yeah, I don't know, it depends. But when you create the filter with the specific capacity and error rate, math will tell you that the error rate won't be higher than that ever, okay? And here's a fun note. Like in the case of Scopely, when you saw the comparison, the 7 gigabytes versus 70 gigabytes, we're using actually error probability of 100 million. So that means that every 100 million, in theory, you're going to have one false positive. And that's a very, very small error rate probability. And now, because we were running this in parallel with the Redis sets, which gives us 100% accuracy, we were able to compare like how many records were being dropped because of false positives. And in our case, it was around 2 records a day. So 2 records a day for 300 million events that you process a day, that's nothing. So.
So how do you define the keys for the bloom filter? Is there a special consideration to keep in mind?
Well, that's also interesting with Bloom filters. You don't need to worry about that. When we were using sets, we actually, our IDs are like these long widths of data. And because they're so long, what we had to do with Redis sets was to rehash them as MD5, so they are shorter, right? And we do some more performance modifications, right? That's Redis sets. With Bloom filters, you can pass any kind of string, like it doesn't matter, because at the end, it's gonna hash this data, and the output of that hash is always the same size. So it doesn't matter really the structure of your keys, right? Because of the data that you're inserting into the set. Because at the end of the day, everything is going to have the same size representation of the hash output.
That means I can store the KBs of keys in the bloom filter that wouldn't impact the performance?
No, like any kind of key that you pass, no matter the size, is going to be like shrink into the size of the output of the hash. So it's not going to have any impact whatsoever.
Any more questions? Okay. So thanks, Christian. And as he said, check out his blog post on the topic as well.